Greetings. I am going to use this reference, A First Step Toward Variational Methods in Engineering by Francisco Piriago, to introduce a physical derivation of one application of differential equations. And these differential equations may be solved by the finite element method. In this video, I'll introduce the equation in one dimension, and it gives an ordinary differential equation. However, an analogous derivation in higher dimensions will give a partial differential equation. The derivation in higher dimensions is similar, so I will present the one-dimensional derivation, and we can use this as a basis for higher dimensional derivations. Okay. The physical application that I'm going to look at is heat diffusion, mentioned here. Okay, so let's move down to page 2 and we can begin. All right. In this case, we're going to consider a cylindrical rod of length L. And that's pictured down here. We have a cylindrical rod. Now the rod is very thin and the cross-section is very small. So we're not interested in the variation across the cross-section, but simply the variation along the rod. So that's what it says here. We assume the length of the rod is much larger than the radius, so we may consider that heat flows only along the x-axis. In other words, we're not concerned about the variation within the cross-section. Now, Fourier's law of heat flow states that the heat flux, which we'll call Q, is proportional to the gradient of temperature U. That is, Q equals minus K U prime. Now let me illustrate that. So I will go ahead and draw a graph. All right, so remember our rod goes in the x direction from 0 to L. So, and we can plot temperature. Now we're using the symbol U as a symbol of temperature. So suppose this end of the rod is hot and this end of the rod is cold. That means the temperature might look something like this. Okay. So we have high temperature here and low temperature here. Now let's consider what's going to happen with this rod. It's well known that heat flows from hot to cold. Okay. So my question is, which direction is the heat going to flow? Well, it's hot here and it's cold here, so heat should flow in this direction. Okay. Now how fast does the heat flow? Well, the hotter this is and the colder this is, the faster the heat flow is going to be. Okay. So the difference between hot and cold here is here. Okay. And the distance is here. Okay. So if we take the difference in temperature, which we can write as delta T, delta U, sorry, divided by the difference in length, which I can call delta X, now we know when the delta goes to 0, we can express this expression as du dx, or that's the same thing as U prime of x. I'll use this notation. Okay. So I'm going to say the larger U prime is, the faster the heat flow. so instead of saying faster, let me say greater. Okay, all right. So I'm going to let Q be the heat flux or heat flow. Now the simplest model of heat flow then would be Q is equal to some constant, which I'll call kappa, times U prime. And that expresses the fact that if Q is larger, that if U prime is larger, then Q is larger. However, notice that heat flows from hot to cold. So here we have a negative gradient of U. U prime is negative, but the heat flow is positive. All right? So what does that mean? That means that we need to have a negative here. Okay? And this kappa will be something positive. Now the other factor I would like to introduce is that the heat flow dependence may vary with x if the rod is non-uniform. So I'm going to write this minus k of x. Okay, so this minus indicates that flows from hot to cold. And this x represents that the rod is non-uniform. Non-uniform. All right. And we also want kappa of x greater than 0. Greater than or equal to 0. All right. So in fact, I should say q of x here. All right. So q depends on x, and we have this law, which is expressed in the reference right here. The x is suppressed. U prime also is a function of x. You should simply remember these things. Now here, they have a minimum conductivity kappa 0. All right, so that's a constraint of the problem. So let's continue reading. This kappa depends on the physical properties of the material and is called the thermal conductivity. The minus sign means that heat goes from high to low temperatures. So we already discussed this. Now, consider a small portion x0, x1 of the rod. That's the portion from here to here. All right, so let me go ahead and copy this so we can see what we're going to do. Okay. All right, so here's a picture of my rod. All right, so what I want to consider is the heat balance within the interval x0, x1. Let's consider the heat balance. Now there's going to be heat flow out, or there's going to be heat flow due to temperature difference, or let me say due to temperature gradient. There may also be a source of heat within this interval. Perhaps there's a chemical reaction, or there may be some external contact with a hot or cold object. So there's also will be heat source within the interval. And these two should balance. Okay, these two must balance. Because you cannot have heat coming in forever, or the rod will become hotter and hotter. And you cannot have heat leaving forever because the rod cannot become infinitely cold. All right. So let's consider these two factors. So first we'll do heat flow. Okay. Now there's the flow that goes out at this end, and then there's the flow that comes in at this end. Now what is the flow that comes out at the right-hand endpoint? So let me just write that down. There's a heat flow out at x1. Okay. So what's that going to be? Well, I have my expression up here. Q of x is the heat flow. Right. Now, since I'm looking at x1, I should say Q of x1. All right. Q of x1 will be equal to minus kappa of x1 times U prime of x1. Okay. So, all right. Now, similarly, I have the heat flow in at x0. Okay. And that's going to be Q of x0. All right. Now, why do I say in and out? Because Q I'm taking as going in the rightward direction, so the heat flow across this small surface at x0 is coming in. The heat flow across this small surface is going out. All right. So that's why I say in and out. So this one here is going to be equal to minus kappa of x0, and that's U prime of x0. Okay. All right, so we have a net heat flow. The net heat flow is simply the heat flow out minus in. So it's going to be minus kappa of x1, U prime of x1. And then I'll have a minus minus, which is a plus. And that's going to be kappa of x0, U prime of x0. All right, now, there's a convenient way to represent this. This is the value of a function at x1, subtracting the value of the same function evaluated at x0. So this is at x1, and this is at x0. Now, by the fundamental theorem of calculus, we know that the difference in function values is equal to the integral of its derivative. Right? So we can write that this way. The integral from x0 to x1 of the derivative of this function, which will be minus kappa of x times U prime of x dx. Now, if you think about the fundamental theorem of calculus, sorry, I forgot the derivative. The derivative of this function. Okay, so if I integrate the derivative of this function, it will give me the difference between the function values at the two endpoints, which is simply minus kappa of x1, U prime of x1. That's the function value inside at the top limit, and I subtract the function value at the bottom limit. Okay, so these two agree, right? This is in fact just exactly the same as this. All right, so then net heat flow is equal to this quantity. Okay. Now I want the heat source. All right, so let's consider now the heat source. So the heat source can be due to different causes. Now it could be external, as I said, an object touching, or it could be internal. And I'm going to express this heat source as a density. Expressed as a density. Now density would have units of heat per length. All right, actually it's heat per time per length. Just like a mass density is mass per length, so heat source density would be the heat source strength, which is heat per time per length. Okay. Now, to get a total mass, you have to integrate the mass density. To get the total heat, you need to integrate the heat source density. So the total heat generated in this interval, the total heat generated in this interval will be equal to the integral from x0 to x1, sorry, the integral didn't come out very well, of the heat source density. Okay. And we're calling that heat source density, we'll call that f of x. So it's the integral from x0 to x1 of f of x dx. All right? Now we need to equate. We need to equate the heat out with the heat source. So heat flow, the heat flow out is equal to the net heat source. Okay? So we can set these two integrals equal, right? The first integral was the one in yellow, right? That's a kappa x prime, sorry, that's kappa. And the heat source integral was here. Okay. Now if I rearrange, I can put both integrals on the same side and put them under the same integral sign, so I'll get this. Integral from x0 to x1 of kappa of x times u prime of x prime, okay, minus f of x dx equals 0. Okay. All right. So this heat balance equation is true for every interval x0, x1. Okay. This is true for every interval. Well, x0 has to be between 0 and L. Okay. Now, we can use a mathematical theorem that tells us if the integral of a continuous function is 0 on every integral. I'm sorry, let me say that again. If the integral of a continuous function is 0 on every interval, then the function itself is 0. Okay. So math will tell us that the integral, if I have g of x is continuous, I'll say CTS for continuous, and the integral from x0 to x1 of g of x equals 0, and that's for all x0, x1. Okay. That implies that g of x itself is 0. I hope this is intuitively clear. But it can be mathematically proven that if you have a continuous function and the area under that function is 0 everywhere, that function itself must be 0. All right? So what does that mean? That means that the function inside the integrand must be 0. Okay? That means that the function that we're integrating, which is this function here, that function must be 0. All right? So I'll just write that here. So we have k of x, u of x, u prime of x, okay, okay, minus f of x is equal to 0. All right. Now I would like to note that this is a linear, second order, one-dimensional differential equation. Now in higher dimensions, you get a similar equation, but you'll get a partial differential equation. Now you can see that what I've done is exactly what's contained in this reference, and we get this same equation. Now this reference says there's an additional term if you have the surroundings transferring heat to the rod. Newton's law of cooling says that heat transfer takes place at a rate proportional to the difference of temperature between the rod and its surroundings. For simplicity, we assume that the surroundings are kept at zero temperature. In fact, we can define zero temperature as the temperature of the surroundings. From this, we obtain the modified stationary heat equation, which has this additional heat flow outward from the rod to the environment that's proportional to the temperature. All right. If U is greater than 0, then the transfer from the rod to the environment is positive. If the temperature is less than 0, then the transfer from the rod to the environment is negative. And once again, we assume that lambda may depend on x. So to sum up, our mathematical model is given by a differential equation, and we also need conditions at the two endpoints. In this case, we're assuming there is no heat flow at the two endpoints. So we call this an insulation condition. All right, so that's the derivation of a one-dimensional heat flow equation, which is a linear second-order differential equation. And as I said, this is a special case which can be generalized to any number of dimensions. If you have heat flow in a surface or a volume, for example, you get a similar equation, but instead of one variable, you'll get multivariables. Instead of an ordinary differential equation, you will get a partial differential equation. Okay, so that's it for this video.